So today our group will present about photoelectrochemistry. Our group members consist of Srinia Lishiminan, Siti Nurfati Nadia, Maureen Anggi, and myself, Patricia Simeon. Next slide. So the contents for our topic, we will cover on theory of photoelectrochemistry, electrochemical cell diagram, process in photoelectrochemical setup, and also factor affecting photocurrent. So first of all, we will cover on theory of photoelectrochemistry. In photoelectrochemistry, it is the interactions between light and electrochemical processes in a system that typically involve a semiconductor electrode in an electrochemical cell. Based on just as we put in the slide, the diagram. So it is the combinations of semiconductor physics and electrochemistry which form the basis for applications like solar energy conversions, photovoltaic cells, and photocatalysis. Semiconductor properties consist of three types, which is the first one is band gap. It is the energy differences between the valence band, which occupied by electron, and the conduction band, which is the empty state. It is for small band gap, it can absorb visible light, such as silicon, while large band gap, it's only absorb UV light, such as titanium oxide. Second one is the N-type semiconductor. It is excess of electron and the conductivity is due to negative charge carrier, which is the electron. And the last one is P-type semiconductor. It is excess of hole, which is a positive charge carrier, and the conductivity is due to positive charge carrier. Next is the photoexcitation process. So the photo effect in semiconductor involve the generations of charge carrier when the material absorbs light. Uh, this, there are three steps of photoexcitations. For the first one, the photon with energy equal to or greater than the band gap energy excite electron from the valence band to the conduction band, creating an electron hole pair called as light absorptions. Next one, the N-type semiconductor in which the electron move to the conduction band and hole remain in the valence band. And the p-type semiconductor, the holes move to the conduction band and electron remain in the valence band. So this we call as separations of charge carriers. And the last one is the charge transport, in which the photoexcited charge carrier move to the semiconductor surface and participate in electrochemical reactions. So the general electrochemical principle in photoelectrochemical cells, we follow basic electrochemical principle in which it involves redox reactions and the movement of electron through an external circuit. So in electrochemical setup, it is consists of two electrodes, which is photoactive semiconductor electrode and a counter electrode, and also an electrolyte solutions. So when the light hits the semiconductor, it generates photocurrent. So the key components of photoelectrochemical cells consist of three. First one is photoanode, which is the N-type for oxidation reactions occurs. For the second one, photocathode, which is P-type. It is for reduction reactions to occur. And the last one is the electrolyte, which support the transfer of ion to complete the circuit. Next, I will pass the presenter to Maureen.
Next, I will discussing electrochemical cell diagrams, specifically on two electrochemical diagrams. Next. An electrochemical system typically includes five main components, which are electrode, electrolyte, container, electrical circuit, and measurement device. There are also supporting equipment such as stirrer, temperature control, and Faraday cage. Next. These are the function of each component. Electrode. In electrochemical cell, there are two electrodes which are site for oxidation and reduction reaction. An electrolyte solution to conduct ion between the electrode it usually contains salt, acid, or base to ion to ion to ionize the ionic conductivity. The third one is a container, often a beaker or specialized electrochemical cell to hold the electrode and solution. The fourth one is next. The fourth one is an electrical circuit comprising a voltage source and or photostat to control electrode potential. Wires are connected to the electrode to voltage source to complete the circuit. The fifth one is measurement device such as multimeter or data acquisition system to measure and record current and voltage, and supporting equipment such as stirrer, temperature controller, and Faraday cage to enhance system stability and performance. Next. In electrochemical cell, reaction occur at both electrode. At working electrode, the primary reaction occur here. The process depend on experimental setup. Either one of the reaction can happen here. If oxidation happen at WE, then reduction will happen at CE or vice versa. These redox reactions are influenced by factors like electrode material, electrolyte composition, and applied potential. Complementary reaction occur at CE to balance the charge and allow current flow. It is necessary to maintain flow of electron. A practical example is water hydrolysis, where the working electrode undergo oxidation and the counter electrode undergo reduction to maintain charge balance. Uh, Refer to the chemical equation, example of the chemical equation in the slide. Next. This is example of photoelectrochemical cell. This is for water splitting, and the detailed processes for photoelectrochemical cell will be explained by my other group member. Next. Let's compare these two systems. First, in terms of energy source, electrochemical cell rely on redox reaction, while photoelectrochemical cell depend on light energy. Next, the electrode material. Electrochemical cell use metal, carbon, and alloy, for example, platinum, graphite, or silver, while photoelectrochemical cell require photoactive electrodes such as titanium dioxide or tungsten disulfide. Lastly, energy goal. The electrochemical cell generate energy from chemical processes, while photoelectrochemical cell harness and convert solar cell. Next. That's all from me.
Thank you, Marilyn. Now I will continue with the process in photoelectric electrochemical setup. So first, photoelectrochemical PEC setup is designed to study and utilize the interaction between light, a semiconductor electrode, and an electrolyte for processes such as water splitting, solar energy conversion, or other redox reaction. For the preparation of materials, there will be four of them: semiconductor photoelectrode, electrolyte solution, counter electrode, and also reference electrode. In semiconductor photoelectrode, we will select a material, for example, titanium oxide or perovskite, which is suitable for light absorption and also charge carrier generation. For electrolyte solution, it uses an electrolyte that facilitates the desired redox reaction, such as H2SO4, or bases, such as KOH. For counter electrode, often a platinum electrode or other materials like carbon or nickel, which complements the working electrode by completing the circuit. For reference electrode, used for potential measurements, such as saturated calomel electrode or AgCl electrode. For the system assembly, light source is very important because a solar simulator or a monochromatic light source is used to mimic sunlight. The intensity and wavelength of light can be controlled to match the experimental needs. For PEC cell, a sealed chamber or an open cell setup where the electrodes and the electrolyte are housed. It includes the ports for light entry, electrodes, and also electrolyte filling. Photoexcitation and charge generation. When light illuminates the semiconductor, photons with energy equal to equal to or greater than the band gap excite the electrons from the valence band to the conduction band, leaving holes in the valence band. This will create an electron hole pairs, which are the charge carriers for the subsequent reaction. Then we will move to charge separation and also transport. The photo-generated electrons are driven towards the conduction band and transported to the conductive substrate, as you can see from the diagram right there. Simultaneously, the holes migrate towards the surface of the semiconductor where the reaction occurs. The surface reactions for oxidation occurs at the photoanode. The water is oxidized to oxygen gas and protons, from 2H2O to oxygen plus 4 hydrogen and 4 electrons. For reduction, it occurs at the cathode. Protons are reduced to hydrogen gas. Then we'll look at the electron flow and also external circuit. As per the diagram, the external circuit allows the electron to flow from the photoanode to the cathode, enabling the continuous operation. If a bias voltage is applied, it assists in overcoming an overpotential required for reactions. For data collection and analysis, there will be two, which is current voltage IV measurement to evaluate the PEC performance, plot photocurrent versus applied voltage. The second one would be IPCE, which is the incident photon to current efficiency, to measure the efficiency of converting photons into electrons. That's all from me. Thank you.
Next, I'll be presenting about the factors that affect the production of photocurrent. Next. There are five factors that affect the production of photocurrent. Firstly, we will look at the frequency of incident light. The frequency of the incident light is very fundamental to the photoelectric effect. When you look at the diagram, you can see that the electron at the surface, it will be excited by the incident light, then they will absorb the incident light and then it will be ejected. The photoelectron will be ejected. This is what creates the photoelectric effect. The relationship between frequency and the kinetic energy of emitted electron is direct. That means higher frequency results in higher kinetic energy for the ejected electrons, which will overall influence the overall photocurrent when combined with intensity. Next, intensity of incident radiation refers to the number of photons striking a surface per unit time. And higher intensity means more photons are available to interact with electrons in the material, leading to a greater number of emitted photoelectrons and thus a higher photoelectrons. However, we need to be careful. While increasing intensity increases photocurrent, it does not affect the maximum kinetic energy of the emitted electron. The energy of photoelectron is solely determined by the frequency of the incident light. Next. Next, we will look at the nature of the material. Different materials have different work function. Work function meaning the minimum energy required to remove an electron from the surface. This will affect both the threshold frequency and efficiency of electron emission. Material with lower work functions require less energy, which means lower frequency to produce photocurrent. Next, we will look at the potential differences between electrodes. The potential difference applied between electrodes can influence photocurrent as well. A positive potential can attract emitted photoelectrons toward the electrode, which will increase the current until it reaches a saturation at certain voltage level. After this voltage level, the current will increase even though the potential has been increased. As you can see from the diagram, this depicts the relationship between potential and frequency. Next. Lastly, we will look at the kinetic energy of photoelectrons. The kinetic energy of photoelectrons is directly related to the excess energy above the threshold frequency. This energy will influence how effectively this electron can contribute to the current flow in the circuit. Higher energy photons means higher frequency can lead to a higher, greater kinetic energy for the ejected electrons. In summary, the production of photocurrent is primarily affected by the frequency of incident light. The frequency of incident light must exceed threshold. Next, the intensity of light means the more photons lead to more electrons. Therefore, the intensity of light must be higher. Next, the nature of the material. It affects the work function and threshold. Fourth, the potential difference across electrons. This will influence the collection efficiency. And lastly, the kinetic energy of emitted electron. The kinetic as I said before, the kinetic energy of emitted electron is determined by the frequency. That's all for me. Thank you.